the role of ND3 substitution on the structural behavior of BI-ND-MnO3. In this, so the topic of my presentation is the solid oxide fuel cells and the synthesis of the BI-ND-MnO3. So ma'am, basically my present work is related with solid oxide fuel cell. Our the current and future necessity of energy has been developed to a variety of alternative sources. There are different types of resources. There are conventional sources of energy, and there is non-conventional sources of energy. But these conventional sources of energy is depleted soon. So we need non-conventional sources of energy, and fuel cell is one of them, non-conventional source of energy. So there are different types of fuel cell: alkaline fuel cell, polymer electrolyte membrane fuel cell, and molten carbon fuel cell, and solid oxide fuel cell. Basically, our work is focused on solid oxide fuel cell. Basically, solid oxide fuel cell is a cell which convert chemical energy directly into electric energy without any combustion. So basically, solid oxide fuel cell has three components. One is cathode, and another is electrode, and electrolyte, and another is a anode. So in solid oxide fuel cell, we supply oxygen at cathode. At cathode, the reduction of oxygen is take place. Then this oxygen is passed through the electrolyte to the anode. At anode, this reduced oxygen combined with hydrogen and give us a steam with the free electron, and these free electron with the help of interconnects can be supplied to the external circuit. So basically, solid oxide fuel cell can be used in various applications, such as in vehicles as an engine and in power generator systems. So basically, we synthesized our material. So basically the title is, I think, misinterpreted. So basically our material is BI-ND-MnO3. So we mixed Bi2O3, NdO3 and MnO2 powder and ball milling them for 6 hours. When the mixed sample is calcined at 700 degrees Celsius for 8 hours, then this calcined sample is again mortar pestle for 5 hours and heated at 800 degrees Celsius for 5 hours. So this is the XRD analysis of our samples. As it is clear from the samples, the sample have a crystalline natures, and the peak we can see their peaks at angle at from 28 to 33. It has a peaks at 201, 121, and 211. So from this XRD analysis, we found that our crystal has a crystalline structure. So this we have made the sample with 3 composition for x equal to 0, x equal to 0.10, and x equal to 0.20. As we can see that the lattice parameter A decreasing, with the substitution of Nd3 plus. So why this happens? The lattice parameter A is decreasing with substitution. This is due to the fact that Bi3 bismuth 3 plus has a 6x square lone pair, 6s2 lone pair. So this, due to this lone pairs, it weaken the local distortion of the lattice, due to which the size of the lattice parameter is decreased. This is the same analysis of our sample A, B, and C for x equal to 0, x equal to 0.10, and x equal to 0.20. As you can see from these samples, same analysis, that with the increasing the substitution of Nd, the particle size, the grain size of our sample is decreasing with our increasing substitution. This is because when we add Nd2O3 in our samples, it restricts it restricted the growth of the grain, due to which it forming more and grains. So with the substitution, the average grain size is decreased, because it provide more nucleating site for the chemical reaction and promoting the more number of the grains. This is the FTIR analysis of our sample. From this FTIR analysis, we found we observed BiO bond present at 500 to 600 centimeter inverse, which is due to the stretching vibration of BiO bonds, which is present in the BiO6 octahedral sites. And we also observed MNO bond, which are observed at 800 to 850 centimeter inverse wave number. We also observed OH bond at 299.5. So these all bond provide a clear evidence that our sample is formed. The conclusion of this paper is that our sample has shown us orthorhombic hydroperovskite structures, and the microstructure analysis of sample show a decrease in the grain size with the increase in the concentration of neodymium. We also from an FTR analysis, from FTR spectra, we have observed MNO and BiO bond, which show the perovskite nature of sample. So therefore, the conclusion is that with the ND substitution, with the neodymium substitution, the average grain size of our sample is decreased, and there is impact on their its structural properties. So thank you.
So I'm going to talk about the low spin iron 3 complexes in neutral monocation and monoanionic form, stabilized by Azo-Appended Tridentate form radicals. So first of all, this is the content part and introduction. Generally, ligands are of two types: innocent and non-innocent ligand. Innocent ligands are those where we can see that oxidation state does not change. For example, during the reduction of MnO4 negative to MnO4 di-negative, the oxide ion ligand, the oxidation state is -2 here and also -2 here. But in case of non-innocent ligand, we cannot predict the oxidation state. For example, catecholate dianion and orthoaminophenolate dianion, it can be -2, -1 or 0. So if we see this orthoaminophenol functionality in acid-base equilibria, which on deprotonase, this functionality first forms this orthoaminophenolate monoanion, which on further deprotonation forms this orthoamidophenolate dianion. Now this dianion undergo redox process. On losing one electron, it forms this orthoaminobenzosemiquinonate radical monoanion, which on losing further one electron forms this orthoaminobenzoquinone form. But the main thing is that when we go from this dianion to monoanion to benzoquinone, there is a change in the carbon-oxygen bond length, carbon-nitrogen bond length, and carbon-carbon bond length of this phenyl ring. So carbon-oxygen bond length changes from dianion to monoanion to benzoquinone, that is from 1.35 to 1.30 to 1.25 plus minus 0.01 angstrom. And this carbon-nitrogen bond length, it changes from 1.38 to 1.35 to 1.30 plus minus 0.01 angstrom. And for a normal dianion, it is the carbon-carbon bond length of the phenyl ring is 1.39 plus minus 0.01 angstrom. And here we can see in case of benzosemiquinonate form, four bonds are longer and two bonds are shorter. So this is a quinoid distortion, and this distortion is more pronounced in case of orthoaminobenzoquinone form. And out of four longer bonds, one bond length will be 1.52 plus minus 0.01 angstrom. And if we see this azo functionality, which can also undergo redox process, and due to low lying pi star orbital, it can accept electrons, forms this monoanion, and further accept the electron and form this dianion form. And these are the well-known non-innocent ligands functionality reported in the literature. And this ligand is reported in the literature. This is a tridentate ligand, oxygen, nitrogen, and sulfur. So it will behave like a tridentate or bidentate depending on the situation which metal is going to bind. So this is the redox scheme of this ligand. Now from this ligand, this metal complex, nickel metal complex was synthesized. So nickel is here and two ligands are coordinating with this metal. So nickel and this nitrogen and oxygen of one ligand and another nitrogen and oxygen of one ligand. So this is 4 coordinations. Sulfur is not binding here. This is sulfur, this is sulfur, so it is not binding here. So 4 coordination. Now after synthesis of this complex, author paid attention to this part, whether the radical is here or the here. Now it is confirmed with the help of crystal structure, and this is the axial crystal data. So we can see here carbon oxygen bond length. This is 1.316 angstrom, and for another ligand this is 1.314 angstrom. And if we see others bond length also, so it shows that one ligand is present in the semiquinone form and another ligand present in the semiquinone form. So -1 is one ligand and another -1 is another ligand. So nickel is in the +2 oxidation state. Now this is the cyclic voltammetry. So cyclic voltammetry, what is it tells? So just a brief idea, but suppose we have that iron 2 complex and we know that iron 2 can be oxidized to the iron 3. So it is a oxidation, and iron 2 can also undergo the reduction iron 1. So it tells about the oxidation and reduction, that is oxidative and reductive behavior. So for this metal complex, nickel complex, is cyclic voltammetry was done. So this is 2 oxidative responses here, first at the 0.29 volt and another is the 0.45 volt versus SC. So 2 oxidative responses and this is 2 reductive responses. So first oxidative response is due to the oxidation of semiquinone to benzoquinone of one ligand, and another second oxidative response is due to the semiquinone to benzoquinone of one ligand. Now similarly for the reductive response, so reductive response, this is due to the semiquinone to dianion of one ligand, because it accepts the 1 electron, it forms the dianion and further accept the 1 electron. So this second reductive response is due to the acceptance of 1 electron by the semiquinone form to the dianion form. Now here we can see E half equal to minus 0.64 volt, and it is almost a reversible kind behavior. So can we isolate this species? So what the author did, that they applied more negative potential here and could see the solution and the EPR behavior. They found this EPR. But what does it mean? That is, if we see this EPR, what is actually is going to be happen? So starting, the complex was like this one, nickel to this semiquinone and this is semiquinone. When this accept 1 electron, so one acceptance of 1 electron accepted by the ligand and it can become the dianion. Now it is maybe a possibility that 1 electron can go to this part, that is metal. So nickel 1 semiquinone form. Now come to the EPR part. So what is actually happening in the solution? So this is 2.0099. So this is due to the radical electron EPR because 1 unpaired electron is present on the ligand. But this part, this 2.0401 and 2.1105, this is due to the presence of this space. So basically in the solution, this nickel 2 and this nickel 1 species is present. So by keeping all these concepts, what I wanted to do, so I wanted to synthesize some redox active ligands, and from those redox active ligands I wanted to synthesize the metal complexes, and then I wanted to see which part of the metal complex is redox active, whether this is metal or ligand. If this is ligand based, then which part of the ligand is redox active, whether in which form, that is in the dianion form or in the monoanion form, or in the benzoquinone form. So I have synthesized a tridentate ligand. The beauty of this ligand is that it has electron releasing part, and this azo part is electron accepting part. So from this ligand, this iron complex was synthesized. I have written here that is the iron 3. How I am confident? Because when I did the MOSBAR, and the MOSBAR data shows that this is in the iron 3 form. I will come to that part because later on this is the MOSBAR data. And now to check the redox behavior of this complex, I did the cyclic voltammetry. So it shows the two oxidative responses. These two oxidative 0.48 volt and 1.06 volt, and reductive responses at minus 0.47 volt and minus 1.48 volt. With the help of this cobaltocene, this is the cobaltocene, it is a reducing agent. So with the help of reducing agent, I could isolate this one electron reduced species, because now you can see here, if I cut this complex here, so there are three oxidative response. So what happens here, in the starting the solution was bluish black. When you add the cobaltocene, it will change into the blue color, dark blue color. So now you got this species. And similarly for the one electron oxidized species, I cut this species here and I got the one electron oxidized species. So from the one complex iron, I got one electron reduced species and I got this one electron oxidized species. The whole thing what I was doing it is in presence of anaerobic environment. Now these are the absorption UV visible spectra. So for the parent complex, and this is one electron oxidized species, this is for the one electron reduced species. All these peaks are due to the charge transfer. And here this is the spectroelectrochemistry. Spectroelectrochemistry means like when you are getting the one electron oxidized species, so what is happening during parent complex to that one electron oxidized species, what is the change in the absorption behavior. So these peaks you can see here for the one electron reduced species, you can see. So there is a change in the absorption spectral behavior. Now coming to this next thing, that we have now three complexes, parent, one electron oxidized and one electron reduced species. But unfortunately I could not grow the crystal of the one electron reduced species. So here this is the crystal structure of parent complex and one electron oxidized species. So carbon oxygen bond length, this is 1.315 angstrom, and here this is 1.307 angstrom. Carbon nitrogen, we see very critically these bond lengths, and for this one electron oxidized bond complex bond length, they are showing that there is some balanced tautomer, like electrons is not fixed at one position, they are highly delocalized from one ligand to the another ligand. How can we prove this? So for this, the time dependent MOSBAR spectra or temperature dependent MOSBAR spectra were done on all three complexes. So this is for the one electron oxidized species, and this is for the one electron reduced species. For the one electron oxidized species, you can see for 80 Kelvin, or also for the one electron reduced species at 80 Kelvin, this spectra is composed of two subspectra, that is one symmetric.
You can conclude now.
Yeah, so just 1.5 minutes only.
Okay.
So with the help of MOSBAR, we can prove the this balanced tautomerin in these complexes. And these are also the supporting data for the EPR for confirming the balanced tautomerin. Now theoretical calculations were done, which where is the electron density is present on the metal or ligand. So it is confirmed with the help of theoretical calculation, that is DFT. And concluding remarks, these complexes were synthesized, DFT was done, and balanced tautomerism is operative for the one electron reduced and oxidized species. And acknowledgement. So this is the acknowledgement. And finally,
So, hello everyone, good evening. I am Anil Rakshe. So, my presentation for the conference is Tailoring Optoelectronic Properties of Hydrothermally Synthesized Tin Dope Nickel Oxide Thin Films. This is the outline of my presentation. Introduction, objectives, synthesis, result discussions, and conclusions. So, introductions to nanotechnology and applications. It deals with the small structures and small size materials with dimensions from sub-nanometer to several hundred nanometers. And the applications of the nano materials in various fields I have drawn here for your reference. So biomedicals, sensors, optoelectronics, high energy batteries, water treatment, energy sources, electronics, optical engineering, etc. So I have focused with the optoelectronics. Next is the objectives of my work is synthesis of tin dope nickel oxide nanostructures, study the effect of this tin doping concentration on nickel oxide nanostructures, study the effect of temperature and pH on the same, study the different properties of SN dope that at tin dope nickel oxide to confirm the phase of SN dope NIO nanostructures by using XRD and Raman spectroscopy. Study the effect of tin doping on morphology of NIO nanostructures using FESM. To study the optical properties of this same SN dope NIO nanostructures. To study the IV characteristics and the photo response of these tin dope nanostructures. Next is this is the basic structures I have drawn for the nickel oxide with the p-type antiferromagnetic oxide semiconductor oxide with wide band gap of 3.6 to 4 electron volt, having conduction band energy 1.8 electron volt, and the different phases it has got like NiO, NiO2, Ni2O3. This is the synthesis procedure that I have carried out for the synthesis of tin dope nickel oxide nanostructures. The nickel salt, nickel precursor, that is nickel chloride, is mixed in the water, and in particular, if I can say about 5% of tin dope nickel oxide, the procedure is this one, that is 0.948 gram of nickel chloride salt is dissolved in 0.0 dissolved in 70 ml of water. Stirring happen at room temperature for say 20 minutes. Then a doping done with the tin precursor like tin chloride, which is added at 0.252 gram, and urea is added into it. Then the mixture was stirred for again at room temperature for 20 minutes. Then the pH of this solution is adjusted by adding sodium hydroxide, and the pH is adjusted to 11. And this mixture, this whole mixture is transferred into Teflon hydrothermal, which is being treated at 120 degrees Celsius for around 4 hours. Then the obtained solution is being centrifuged and washed by distilled water and ethanol for 4 times, and then this the precipitate octane is dried in the oven, and then that same powder is being calcinated at 500 degrees Celsius in the oven. See, this is the image, same image of the one of the sample which I have got is shown here. The results and discussions. The first characterization I did for my sample is XRD, and I prepared the plain nickel oxide solution, nickel oxide nano structures, nanoparticles. The XRD curves was something like this. Then the doping done with the tin nickel oxides like 1.25%, 2.5%, 5%, and 10%, and their XRD results are like this. So these XRD results shows that there is no any impurity. The peaks are obtained at 111, 200, 220, 311, and 222 HKL values. Then the Raman spectra for this 5 samples is like this. or this one is in black color is for nickel oxide, and this is for the different doping concentration of tin dope nickel oxide nanostructures. These are the same images which I have carried out for the different concentrations. This is for pure nickel oxide, and these are for 1.25% of tin dope. This is for 2.5, 5%, and the 10% tin dope nickel oxide. So the results reveals the different structures for the different concentrations of tin doping into the nickel oxide nanostructures. This is the EDS data analysis for all these 5 samples having percentage weightage of nickel, oxygen, and tin. The UV visible spectra for all these 10 samples was analyzed for different nickel oxide and different concentrations of tin dope nickel oxide, and the absorbance peak are observed at different values. These are the IV characteristics which I have obtained for the nickel oxide and different concentrations of the tin dope nickel oxide nanostructures. So again, here also the different efficiencies for the different types of the tin dope nickel oxide nanostructures was being significantly observed. These are the photo responses being recorded by the current and time curve. So this is again the photo responses for nickel oxide and the different concentrations of the tin dope nickel oxide nanostructures. The conclusion of my work is hydrothermal process was used to synthesize the tin dope nickel oxide nanostructures. The effect of doping on concentration of tin was studied, and the effect is the size and shape of the nanostructures were affected by the doping, which also had an influence on the formation of tin dope nickel oxide. The characterization results revealed that the tin dope nickel oxide nanostructures have formed in the FCC cubic phase, and the IV characteristics of nickel oxide thin films increases upon the doping of the tin. It is likely that these nanostructures can be used in solar cells, optoelectronic applications, photocatalysis, capacitor devices, tune circuits, and the lithium-ion batteries like that. But my work is basically concerned with the in the solar cell. So I am studying this particular application of tin doping on nickel oxide into the solar cells. Thank you, sir.
Well,
Thank you so much.
I am Dr. Anita, presently working as a assistant professor in Guru Nanak College, Shri Muktsar Sahib from Punjab. This college is affiliated to Punjab University, Chandigarh. And my topic of presentation is study of structural stability and ferromagnetism in chromium doped gallium phosphide semiconductor by using a density functional theory. This is a totally theoretical research, as we know that the theoretically condensed matter physics materials has been divided into 4 categories, and these are in form of clusters, fluorines, dilute magnetic semiconductors, nanotubes, and nanowires. Out of them, today I will discuss about the dilute magnetic semiconductors, and these are the new magnetic materials and have vast applications in nanoelectronics, in sensors, and in opticals and magneto-optical devices. First, we would like to discuss what are the DMS. DMS, as we have mentioned, dilute magnetic semiconductors. Every word has their own meaning. Why we called it them dilute? Because here we have added a small amount of impurity atoms. So that's why it is called dilute. Magnetic, because the transition metal that we have added produce the magnetic effects and magnetic moment on the non-magnetic atoms, and during the doping the semiconductor behavior remains preserved, so that's why these are called the dilute magnetic semiconductor. And in here DMS are the solid solution in which semiconductor component is partially replaced by the magnetic transition metal, and the material partially fill 3D orbitals of metal atom and supply a variety of spin dependent properties. depends upon two main phenomena. One is the exchange interaction between the local movements, and second one is the charge carriers. DMS are the fundamental materials for spintronics because of their compatibility with the semiconductor used in the electronics, and DMS are expected to play an important role in material science and in future electronics because charge and spin degree of freedom accumulated into a single material exhibiting interesting magnetic optical and magnetoelectronic and other properties, and these material can exhibit a wide range of magnetic properties from paramagnetic to spin glass behavior and even to ferromagnetism. So as we know that in the traditional electronic devices that are used, they ignore the spin property and rely only on the electrical charge of the electrons. So combination of semiconductor technology with magnetism give rise to a new type of devices. These are called the spintronic devices and might lead to the quantum computers and quantum communication based on electronic solid state devices, thus changing the perspective of information technology in 21st century. What are the advantages of the spin? In case of spintronic devices, as we know that information is stored into spin as one of the two possible orientation, and spin lifetime is relatively long, of the order of nanoseconds. Spin current can be manipulated. Spin devices may combine logic and storage functionality, eliminating the need for separate components. And magnetic storage is non-volatile in nature. And binary spin polarization offer the possibility of application as qubits in quantum computers. Other advantages, these are smaller in size, more versatile, more robust than currently used silicon chips, and circuit elements enhance the functionality, higher speed, and reduce power consumption. But as compared to their advantages, but there are two main limitations of these type of devices. First one is the solid solubility. As we know that the magnetic behavior of semiconductor, solid-based magnetic semiconductor is totally dependent upon the concentration of the magnetic material. So if we add large amount of magnetic atom inside the semiconductor material, the metal atom will form new type of complexes. So, but if the concentration of magnetic impurity will be very, very small, then it will be very difficult to achieve the Curie temperature at room temperature level. So this is the main problem, that we have to find out the devices or materials which have the Curie temperature at the room temperature. So as this theory is, these type of calculations are totally theoretical, and there are so many approximations has been used to sort out the many body electron problems. First one is the Born-Oppenheimer, and then Harte-Fock. After that, there is functional theory which we have used in this in present work, and here we are taking only the electron-electron interaction. That is, we are dealing with only the valence electrons, not the core electrons. And core electrons has been freezed, and as their wave function is very changing in nature, so that's why they have been replaced here with the help of a pseudo potentials. And to sort out the wave functions, basis set has been used. So what is the density functional theory? It replaces the many body electronic wave function with the electron density as the basic quantity, as electron density is depend only upon the three variables only, as there. But previously, many body wave function depends upon the 3n variable. So the first density function theory was developed by the Thomas and Fermi in 1920, but it was put on firm footing by the Hohenberg and Kohn. So these are the pseudo potentials that we have used to freeze the effect of the core electrons, and basis set are used to for the mathematical representation of the electron orbitals. So the Siasta is a code which is used to sort out the calculations to find the electronic properties, magnetic properties, and structural properties of the studied materials. What is Siasta? The full form is the Spanish initiative for the electronic simulation with thousands of atoms. During the calculations, we have fixed some parameters and used the exchange correlation functions. And here we have used the local density approximation and local density approximation plus UU is the Hubbard parameter, that is exchange correlation potential has been used. First, we have prepared a standard unit cell of 1 by 1 by 1, and second supercell we have used is the 2 by 1 by 1, in which we have replaced the one atom of semiconductor material with the transition atom, and to simulate the different type of concentrations, that is 0.25, 0.125. Energy of 80 millielectron volt is used to define the real space grid, and 4 by 4 by 4 Monk host tag grid has been used, and atomic positions as well as lattice parameters are allowed to relax until the forces are smaller than 0.04 electron volt per angstrom. And pseudo potentials that we have used are constructed using the TM parameterization scheme. First, we have find out the structural properties of chromium gallium phosphide. First, we sort out the find the parameter for the pure material, and after that we have done the calculations for the material. For pure material, we have used the different values of lattice constant in the range of experimental value, and then by using a Morgan equation of state that I have mentioned here, we have found out the following parameters like lattice constant, bulk modulus, and the band gap. So this is the energy band diagram of the pure semiconductor material. It shows that there is a gap between the valence band and the conduction band. This means the pure semiconductor material shows the semiconductor behavior, and it also we have found out from the total density of states. But when we dope the chromium
Please
atom
conclude.
inside the, then
Please conclude.
sure, sir. After doping, it shows that in the minority channel, the band gap crosses the Fermi level, but in case of majority channel, there is a gap. So system shows a half metallic behavior. These are the partial density of states, and these are the parameters that we have used to find the magnetic properties of the materials. And from the magnetic properties, we have found that the beryllium and phosphorus both are the non-magnetic material, but when they are doped, they show some magnetic movement. So that's why this system show a magnetic properties. The main cause of magnetization is due to the availability of 3D state of chromium atom. The study of PDOS of 3D state also showed that magnetic property arises due to the strong hybridization of partially filled 3D state chromium with S and P state of phosphorus atom. Hybridization of chromium 3D and P states causes induction of local magnetic moments on the non-magnetic atoms. So that's why total energy of the system decreases and their exchange interaction occurs inside the host materials. So the major challenge is the same here, that we have to find the
some material. So basically the Seebeck coefficient is denoted by S, which is nothing but the slope of the curve between the temperature gradient and the thermoelectric voltage generated. So minus VTH by delta T is the Seebeck coefficient. So what material do we need to choose to make a good thermoelectric material? So first of all is the power factor and the device efficiency, including the figure of merit, are the important parameters. So these are determined by materials, electrical conductivity, thermal conductivity, Seebeck coefficient, behavior under changing temperature. So ZT, basically the figure of merit, is dependent on...
Slides are not moving.
Slides are not moving? Okay, sir, I'll just... Sir, is it visible now? Is it visible now, sir?
Yes, visible.
Okay, sir. So these properties are basically determined by the electrical conductivity, thermal conductivity, Seebeck coefficient, and there has to be a trade-off between all these parameters so that we can get the maximum ZT value, that is the figure of merit, and it is dependent upon sigma s squared T by K, which is where sigma is the electrical conductivity and S is the Seebeck coefficient, T is the temperature, working temperature, and inversely proportional to the thermal conductivity. So for a material to process a good thermoelectric properties, so it should have large Seebeck coefficient, high electrical conductivity, lower thermal conductivity values. So we have to satisfied by these has to be satisfied by low dimensional parameters. So due to the small Seebeck coefficient, metals have very limited performance, and the main material of interest these days are the semiconductor materials. So there are variety of semiconductor materials which have been exploited till now, like lead telluride, antimony telluride, and these have high ZT value at room temperature but are very toxic and expensive and are low in natural abundance. So another material which is gaining popularity is the tin selenide. It has very high ZT value at around 923 Kelvin, and also it has very high cost production. Another material, cobalt, cobalt, bismuth. So cobalt has the moderate scatterite which are earth abundant, eco-friendly, but are prone to oxidation. But these days, indium selenide and bismuth tellurides have been widely explored. So these have high ZT value near room temperature with high electrical conductivity, high mobility, low thermal conductivity, which also reduces further on decreasing the thickness. So from bulk, now we are moving towards the thin film, because thin films are first of all less explored, and also the thin films pay provides a way towards the nanotechnology. So we have the flexible thermoelectric generators also these days. So these flexible thermoelectric generators are produced in the form of fabrics or flexible modules. So thermoelectric generators paves a way to harvest energy from waste heat and offers a clean energy source for increasing demands and decaying fossil fuels. Flexible substrate could provide an easy platform to integrate. मम्मा की मीटिंग चल रही है, नीचे ले जाओ. So to provide an easy platform to integrate with any device, and thus could be utilized for self-power generation in electronic circuitries. And flexible thermoelectric generators can also harvest body heat to charge the wearable electronics and sensors. And also another recent approach is the utilization of fabric made up of thermoelectric materials. And India, there is a big market of procuring energy harvesting devices from other developed countries. So, thus, the focus of the present work is towards the development of thermoelectric energy harvesters on flexible substrates as well. So, the process flow includes first the film growth using the thermal evaporation, then studying the surface and structural morphology and optical measurements of the deposited thin films. Then we studied the electrical conductivity using indigenously developed Hall setup and thermal conductivity using the 3 omega method of the prepared thin film, and then finally studying the thermoelectric properties of the developed thin film using the indigenously developed thermoelectric measurement setup. So first of all, the effect of post annealing of indium selenide thin films have been seen using these films have been grown using the thermal evaporation, and the XRD pattern indicates that there is a transition from 104 plane of indium selenide to 006 plane of gamma phase of indium selenide from as grown film to the films deposited at 300 degrees Celsius. Now, this is the Raman spectra, and this on the right hand side, Raman spectra shows the transition from 114 centimeter inverse for alpha indium selenide to 150 centimeter inverse corresponding to the gamma indium selenide. So, as the any post annealing temperature is increasing, the film phase is changing from alpha to gamma phase of indium selenide, which is more beneficial for the thermoelectric properties. So there are the AFM studies also, and the UV visible spectroscopy shows that the band gap of the film increases with the increase in the annealing temperature, and AFM and the FESM images shows that the surface roughness increasing with the annealing temperature up to 300 degrees Celsius, and on further increasing the annealing temperature, it starts to decrease. And also the EDEX studies highlight that the composition of indium selenide with a decrease in amount of selenium with an increase in the annealing temperature. So the thermoelectric measurements have been performed using the indigenously in-house developed setup, and the carrier concentration and the mobility are calculated using the Hall measurement, and the thermoelectric measurements were carried out using this setup for the films annealed at 250 degrees Celsius, 300 degrees Celsius, and 350 degrees Celsius, with one end fixed at room temperature and other end is heated to 150 degree Celsius. So it can be seen that as the post-annealing temperature is increasing from 250 degrees Celsius to 300 degrees Celsius, the thermoelectric voltage generated is increased up to 12 millivolt. Likewise, on the cooling stage, when we cool down the sample from higher end 150 degrees Celsius to room temperature and reduce the temperature difference, we are again seeing the same pattern. So we have evaluated the Seebeck coefficient and the power factor, and it is found that the Seebeck coefficient is maximum for the film deposited at 300 degrees Celsius, which had the gamma phase. Now we have to investigate the thermoelectric conductivity. We are using the 3 omega method, and for that we have prepared a heater using the photolithography technique using the maskless lithography over the thin films. And these are the thermoelectric measurement using the 3 omega method, where we have prepared a heater pattern using the photolithography over the thin film and utilize this as one of the resistance in the we have utilized this as one of the resistance in the Wheatstone bridge configuration. Thermoelectric conversion efficiency of the material have been evaluated, and it was evaluated that 300 degrees Celsius film shows the maximum efficiency up to 0.85%. And then the the thermoelectric properties have also been studied for bismuth telluride and antimoney telluride thin films and these films have been prepared again using the thermal evaporation, and the material has been prepared in-house using the hydrothermal process. And these are the characteristics studied for the bismuth telluride and antimoney telluride material, and these are the SEM images of the bulk material, and these are the XRD pattern of the bulk material, and these confirm the formation of bismuth telluride and antimoney telluride using the hydrothermal technique. And then we studied the thermoelectric measurement using the again indigenously developed setup using these thin films, and we found that the antimoney telluride and the bismuth telluride gives the comparable voltage which have been generated up to 40 millivolt, and for bismuth telluride it is 45 millivolt. So we evaluated the Seebeck coefficient, electrical conductivity, and the thermal conductivity and figure of merit for both the materials, and compared that the bismuth telluride is giving the better result as compared to the antimoney telluride. Now then we tried some doping in the bismuth
Okay,
telluride.
Dr. Anjali Sharma, please conclude your work in 2 minutes.
Yes, it's done. Almost done. So we have incorporated silver, cobalt, and lead, and the values of Seebeck coefficient was not found to be much impressive in this case. So we further fabricated bismuth telluride thin film on the flexible substrates like polyamide, and we found that the voltage generated in the polyamide surface is around 100 millivolts. So the substrate is also playing a key role in creating the temperature difference and the voltage generated. So then we also exploited the metal oxide thin film for the thermoelectric energy harvesters, and these are the results for MOS2 2D layers incorporated with the iron doped zinc oxide. So we also found that in this case the configuration where the sandwich is made between the MOS2 layer and the zinc oxide thin film, iron doped zinc oxide thin film, give the maximum voltage generated up to 20 millivolt. And again, the figure of merit is comparable with that of the bismuth telluride thin film based substrates. Thin films. So we have, in conclusion, we have studied the indium selenide thin film, bismuth telluride and antimoney telluride thin film, and metal oxide thin film for making the thermoelectric energy harvesters. Thank you so much.
To all the session organizers and all the eminent delegates who attended the next session. I'm Arijit Chowdhuri. I'm teaching in the college, Ashok College in University of Delhi. The topic of my presentation today would be highly efficient, low temperature operated NO2 gas sensors. So the first outline of the talk, the need for gas sensors and why NO2 gas and why have we used tin oxide based thin film based gas sensors. Finally, how do we take this thin film based gas sensors into MEMS configuration? And finally, if time permits, the 2D MOS2 layered based gas sensors. I think I won't be able to go till that. I'll just try to end my talk till the MEMS based gas sensors and the packaging. Now, the need for sensors. Sensors, what is a sensor? A sensor is a measuring device that senses a stimulus and converts it into measurable output in a tandem way. Three types of sensors, basically the physical, chemical, and biological. In physical, we have the pressure sensors, acceleration sensors, temperature sensors, and magnetic field sensors. The chemical sensors, of course, the gas sensor, the topic of my presentation today, you have photodetectors, we have electronic nose. Electronic nose consists of multiple sensors which are configured to perform gas sensing. Finally, the biological type sensors, they constitute the one that we have worked in our lab is the cancer, the meningitis, uric acid, urea, and cholesterol. The need for gas sensors is multifold in India because air pollution in India has risen more than 13% in the last 5 years. The increasing population demands, the increase in industrialization, and also anthropogenic requirements demand more and more automobiles. This has led to destruction of vegetation and formation of concrete jungles. The airborne particles and toxic chemicals that make up the smog, especially in cities like, let's say, Delhi and NCR, is like smoking more than 50 cigarettes a day. And most cities in India are failing to meet this national ambient air quality standards in AQS by a wide margin, which anyway have a lower tolerance compared to the European standards. So what basically causes this air pollution? We have natural processes and mostly human or anthropogenic activities that have changed the rate of energy absorbed by the atmosphere. The human sources include increasing concentration of greenhouse gases like methane, carbon dioxide, which are able to trap the heat, deforestation and land use changes, sulfate aerosols, soot particles. Natural sources, which are not that much in this part of the country, but at other places, there are volcanic eruptions. We also have natural aerosols, variations of solar output, especially at the poles, and wildfires in the forests in countries like America and Australia. So what are the solutions to the air pollution? To use renewable fuel and clean energy that includes alternative use of sources of energies, including solar, wind, and geothermal instead of fossil fuels. Use of eco-friendly transportation. We look into fuel cells, lithium-ion, or similar kinds of batteries to power various modes of transportation. Green buildings, of course, make the buildings green. And air quality index, as we keep reading in day-to-day, especially in the northern part of the country, they are at the breaking points. So why emphasis on nitrogen dioxide? That's because the effect of nitrogen dioxide, or rather I would say ill effects of nitrogen dioxide, is manifold in the environment. NO2 gas is a precursor for ozone at lower atmosphere, that is the troposphere. Ozone is a secondary pollutant not emitted by any specific source, but rather it is formed due to reaction of NO2 gas emitted from automobiles, which are increasing from day to day. And when they react with sunlight, they create this NO. The ozone in the lower atmospheric region is causing global warming, and NO2 gas also reacts with water vapors that are present in the atmosphere to form nitric acid, leading to precipitation in the form of acid rain. So hence, NO2 detection finds importance in day-to-day life of humans. So what are the features that one looks for in an efficient and a good gas sensor? Number one, it should have high sensitivity towards a particular gas, in this case, NO2. It should have a quick response time. It should have a faster recovery and should have reproducible characteristics. It should be operating at a very low operating temperature.
Dr. Arijit, sorry
Yes,
for
please.
the interruption.
Yes, sir.
Your slides are not moving. So please click on the slide that you want to display.
All right. I'll just go back and I'll just do it. I'm sorry if this has happened. Right. So I think I've gone further. Okay. So I'll just, is this slide visible, sir?
Yeah, it's fine.
Yeah. Thank you. So why do we need nitrogen dioxide gas sensors? And the first thing we already discussed is mainly to do with the formation of ozone, and besides that, of course, precipitation in the form of acid rain. So effectively, we need to design faster and faster sensors, and some of the features that we look for in an efficient gas sensor, in this case an NO2 gas sensor, is that it should be highly sensitive towards NO2. It should have a quick response time. It should have a fast recovery and should exhibit reproducible characteristics. It should have a low operating temperature, mainly point of view for industrialization. It should have a low direction limit, and it should be highly selective, that it should show effective partial selectivity towards NO2 with whatever material we design the sensor with. So list of semiconducting metal oxides and the targeted gases that are available from the literature, and we find that tin oxide typically shows, or rather detects, most of the gases. So advantages include their high chemical stability. It has easy absorption of oxygen on its surface. It is highly sensitive, low cost, and it exhibits quick response and recovery. But the main disadvantage that tin oxide suffers from is that it is prone to strong interference effects from other gases, and that leads to poor selectivity, and it has a higher operating temperature compared to other metal oxides. Semiconducting nature, semiconducting metal oxides. So in our study, what we have done is we have fabricated or synthesized the tin oxide thin films using RF magnetron sputtering, wherein we have used a tin target and RF sputtered it at 13.56 megahertz in argon oxygen ambient. We had some of the typical optimized parameters are shown here. We have used a Corning glass substrate, which has interdigital electrodes lying underneath. We have a typical target substrate distance of 7.5 centimeter, 150 watts of power, and pure 4-inch tin target, having almost 99.995 purity. And we have varied the sputtering pressure from 12 to 18 millitorr. I'll show you the graphs and how we have optimized it. We also varied the oxygen gas concentration from 20 to 50%. All right, so typically shown here are the XRD and AFM images of tin oxide thin films. During optimization, one of the few things that we took care of was that the film should be kind of porous, but not too porous, because that affects the recovery. And of course, it should have a nanocrystalline structure so that it offers more and more surface area for detection. So we found that we spotted the films at 12 millitorr, 14, 16, and 18 millitorrs. And as you would find that for gas sensing, of course, we use this customized gas sensing test rig, wherein it had a computer interfaced Keithley DMM. And we had a chamber which could actually simulate the real life conditions. Like, for example, we put in 0 grade air, and we put the target gas in a specified calibrated leak. And we took out the measurement characteristics, including sensing response, the response time, and the recovery time. All right. So going back to this graphs, the effect of we initially investigated the effect of growth conditions on sensing response. First was the sputtering pressure, and you would see that that around 16 millitorr we had the best response, sensing response, and with that we also varied the oxygen concentration, and we found that 70% argon and 30% oxygen gave us the best response. And thickness also we varied, and with varying thickness we found that 430 nanometer thick film of tin oxide gave us the best response. Moving forward. I'm not going into the what you call the mechanism, because that's already published in our papers. So we found that in order to improve upon the sensing performance of tin oxide, we made heterostructure sensors, and for this we investigated various catalysts, and the effect of catalysts can be seen here. We found that the sensing response increased by about 2 orders of magnitude, and that too for a very low concentration of NO2 gas. And we found that tungsten trioxide. As you can see here, tungsten trioxide exhibited the best response at a low operating temperature of less than 100 degrees Celsius, and which offers.
Dr. Arijit,
Yes, please.
Please conclude.
Yes, please. I'll just conclude in 3 slides. Yeah, thanks. We found the best response time and the recovery time. So moving forward, we optimized the deposition of tungsten trioxide using a PLD, pulse laser deposition, and finally we incorporated this into a package, and the package sensor that is we have developed and published also in our journal. The results are published already over here. So we found that, okay, fine. We have this package sensor with tin oxide having tungsten trioxide as a catalyst for detection of nitrogen dioxide gas, not at room temperature, but a little bit higher room temperature, around 80-85 degrees Celsius. Thank you very much.
Okay. So, thank you, madam. Good evening to all of you. So myself, Dr. Ashok Kumar, I am assistant professor in the Department of Physics, Deenbandhu Choturam University of Science and Technology, Murthal, Sonipat, Haryana. So today I am going to present some results on sol-gel synthesis of lanthanum ion doped nanoparticles and their application for the efficient removal of rose Bengal dye in the wastewater treatment. So these are the outline of my presentation: introduction, the sample synthesis I will discuss, then results and discussion and conclusion. So as we know, the water pollution is one of the major problem nowadays. Basically, the different type of organic pollutants such as this from the pharmaceutical industry, from the textile industry, these different types of chemicals or color dyes, these are being discharged into the water without any treatment.
Sir, I think your slide is not moving if you are changing.
Yes, madam,
Yeah,
I am
okay.
changing.
Yeah, okay. Now it is moving. Okay.
So if I'm making it full screen, is it changing or not, ma'am?
Even full screen is not coming.
Okay.
So you can just click on the slide and you may continue with that.
Okay. So different type of these organic pollutants such as dyes, these are being discharged into the water without any treatment. And these dyes are very harmful, toxic in nature, and that causes a significant risk to the aquatic life and the public health. So due to the outflow of these dye effluent from different type of industries operations, so the dye pollution is a severe environmental issues. Now the problem we have, the wastewater. So different methods are available to treat this wastewater in order to remove these organic pollutant or the dyes. So there are different methods for the removal of dyes, which the one is physical methods, which includes screening, sedimentation, filtration, and the chemical methods, including the chemical precipitation, coagulation. But there are some limitation of these methods. First one is the efficiency. With these methods, we cannot remove the 100% these pollutant or dyes from the wastewater. And the second one is the byproduct. These byproducts are the toxic in nature. So then we adopt the advanced treatment methods, which involve the advanced oxidation process. In advanced oxidation process, there are again different of type of methods are here, like ozone-based process, plasma-based process, electrochemical oxidation, and the one is the photocatalysis. So from all these methods, the advanced oxidation methods, so this photocatalysis is considered as a most promising technique. The reason is the technique is highly efficient, and the byproducts, these are such as carbon dioxide, waters, minerals, etc., and these are non-toxic in nature. And another point is there is use of renewable solar energy. Visible light can be used. in order to break these harmful organic pollutants which are present in the wastewater, and then we can convert them into the harmless product. So this is the basic mechanism of photocatalysis. This is the energy diagram of the catalyst having the conduction band, valence band. Then when the light falls on the exposed on the material, so there is transfer of electron from the valence band to the conduction band. So we have electron hole pair generation is there. So these holes interact with the dyes and produce these holes react with the water and produce OH radicals, and electron react with the oxygen, produce the oxygen radicals. And these radicals, they directly interact with the dye and then further degrade the dye, and the final product which we will get, these are the carbon dioxide and water. So in order to remove these dye, different type of materials are available, and the main are the metal oxides. Zinc oxide, cerium oxide, SnO2, TiO2, lots of metal oxides are available. But there is some limitation for using these metal oxide nanoparticles in the wastewater treatment. The one reason is the large band gap, and we cannot use them for the visible light. And the one parameter is the fast recombination of the electron hole pair, so that we not get to so much efficiency for the removal of dyes from the wastewater. And again, these are less magnetic in nature. So in order to improve their efficiency, what we do, we drop the rare these metal oxides. For example, I have taken the case of SnO2. So we have doped the SnO2 with rare earth elements. So by doping the rare earth elements in the metal oxides, what will happen? There is creation of defect levels, which reduce the energy band gap. And there is a reduction in the char carrier recombination rate, because some type of impurity levels or some energy sub-energy levels will create in between conduction band and valence band, so which traps these radicals, and their recombination of the charge carrier is not so fast, so that radicals can be used in the degradation of dyes. Also, there is some induced magnetic nature in the samples. So based upon this, I have selected the SnO2 nanoparticles and doped them with lanthanum ion, and we have prepared a series of lanthanum doped tin oxide nanoparticles with the 0, 0.5, 1.5% and 5%. We have prepared the sample by using sol gel method. Basically, lanthanum nitrate and tin chloride, these are taken as a starting material, dissolve them in ethylene glycol, stir them for get homogeneous solution. The solution was then with constant stirring heated at 120 degrees Celsius for 3 hours. Then we get the gel type formation. Gel was then heated at 170 degrees Celsius to get the powder. The powder was further grinded and annealed in the furnace at 600 degrees Celsius for 2 hours, and we get the final nanoparticles. Now, to know the structural, magnetic, optical, and properties of these synthesized nanomaterials or materials, we characterize them by various techniques. First one is the X-ray diffraction. So all the sample shows single phase, all the peaks corresponding to the single phase without any trace of impurity. We have calculated calculated the crystallite side using Scherrer formula. The lattice parameter is increasing. We can see the lattice parameter is increasing with lanthanum ion concentration. The reason is we are replacing Sn by lanthanum. So lanthanum has larger ionic radii, so there is, as compared to Sn ion, so there is expansion in the lattice. So this expansion causes the creation of defects in the lattice, and these defects are responsible for the improvement in the properties of these materials. So we have done this is the Rietveld refinement. Again, we have calculated using the Rietveld refinement these structural parameters, and these are in close agreement to which we have calculated from the XRD results. These are more accurate. So another spectra shows the vibrational bands corresponding to the SN oxygen, SNO, SN stretching vibrations, and there is symmetric vibration of SNO, SN bond in the lower wave number side at 488 centimeter inverse. In addition, there are 2 or 3 bands at 3400 and 1600, which are due to stretching vibration of OH or water present in the sun. These are the ICRTMD results. Particles are spherical in nature. We have these are particle size we have calculated lies between 14 to 11 nanometer, and we have the narrow size distribution of the particles. From higher resolution images, we have calculated the interplanar spacing for the plane, and the d value which we have calculated are same as we have calculated from the XRD pattern. So the conversion of the replacement of SN by La ions and the creation of the oxygen vacancies or different states of the elements which are present in the sample that we have confirmed from the XPS. This is the XPS results for 0% lanthanum and 0% lanthanum for oxygen 1 state. This is for 5% lanthanum oxygen state. We can say the area under the peak is more in case of 5% lanthanum ion, means there are more oxygen vacancies. And this is the 3D spectra of 5% lanthanum, that indicating that there are 2 states of lanthanum, 3D 5/2 and 3D 3/2. Such peaks are not observed in case of 0% lanthanum. So this is the another confirmation of presence of lanthanum in the sample. So as we can see here, the area under the curve is increasing. I'm audible, ma'am?
Yeah, you are audible.
Okay. So we have calculated the energy band gap of these nanoparticles using UV DRS spectroscopy, and the band gap is decreasing from 3.74 to 3.51 with the increase in lanthanum ion concentration. So the reason for decrease in band gap is the creation of new sub-levels in between the conduction band and the valence bands. These are the defects or some energy levels that are being created by incorporation of the lanthanum ions. So these are the magnetic measurements results. We can see the sample shows weak ferromagnetism at room temperature, and for the sample with 0% lanthanum ion, we have the less magnetization, and the magnetization is increasing with the increase in lanthanum ion concentration. So these are the photocatalytic activity results for the degradation of rose Bengal dye. So we have what we have done here, we have taken the solution of RB dye, and we have taken small amount of these catalyst and perform the absorbance results for UV for different time interval after 15 minutes. So we can see here the sample with maximum lanthanum content that shows the degradation of RB dye to the maximum extent as compared to the sample having 0% of lanthanum. So we can see here the dye degradation, the concentration, relative concentration of dye is decreasing with time and the maximum degradation has been observed in the sample with maximum, that is 5% lanthanum ion. And we have calculated this electrical energy per order for time t 90 minutes, and this is also decreasing with the lanthanum concentration. So this electrical energy per order is minimum for the sample with 5%. And we can see here, we have also calculated the electricity cost in Indian rupees based upon the what is the price unit we have in our area. So this is 1.019 Indian rupees for degradation of dye up to 94% in 60 minutes with the sample having 5% of lanthanum. Again, we have studied the reusability of these nanoparticles. The sample for 5% lanthanum, we have performed the reusability test for the 4 cycle, and we can see in the 4 cycle also we are getting 87% degradation of rose Bengal dye for using these nanoparticles. And this is the another test, that is a squenger test performed for benzoquinone, 2-propanol and EDTA. And we can see here in case of RB dye, these OH radicals and holes, mainly these are responsible for the degradation of the dye, because in benzoquinone it capture the oxygen radicals. So oxygen radicals it is capturing. So again, we are getting the degradation efficiency is high. So I can conclude that we have successfully synthesized lanthanum ion doped SNO2 nanoparticles using Sol gel method. Crystallite size lies in the range 9 to 12 nanometer. The structural conformation was done again using the FTIR and HRTM spectroscope, HRTM images. And the saturation magnetization increases with lanthanum ion concentration. So there is increase in the band gap from decrease in band gap from 3.74 to 3.51 with the lanthanum ion concentration, and we have obtained nearly 90% degradation of rose Bengal dye in 60 minutes under UV light irradiation for catalyst with 5% lanthanum. So thank you very much for giving me this opportunity to present my work.
I will discuss many additives like organic solvents, glycols, and all that, salts also. Co-surfactant, if any co-surfactant is another surfactant is present, then also the CMC is affected. As well, lastly, it is the temperature which also affect the aggregation of the surfactant. Various actions of surfactant. These surfactants are used industrially in large number of applications, including reducing the surface tension, improving the wettability, providing cleanliness, solubilizing the oils in water or hydrocarbons in hydrophilic portion, stabilizing the any films, or modifying the surface and other properties. Now, micellar behavior surfactants in presence of polymer. First part is how the surfactant form micelles in presence of a polymer. For example, I have taken the two surfactants like sodium caprylate and cetylpyridinium chloride. First one is an anionic surfactant, other one is a cationic surfactant, and these are their structure. Along with the polymer polyvinyl polaridone, it is a non-ionic polymer. These are their structures. Now, these interactions between the polymer and surfactant are significant for applications in various industrial uses like paints, coatings, adhesives, detergents, cosmetics, foods, and pharmaceuticals. This is how they interact with each other. This is the various symbols of polymer, surfactant, and the micelle. The polymer interacts with the surfactant due to hydrophobic interaction. When these hydrophobic interactions increase, the surfactant molecules come closer to the polymer backbone, and then they form aggregates around the polymer. And when this concentration becomes more, then they form micelles in the solution also, or in the liquid phase also. So that is called as the PSP or polymer saturation point. After the polymer saturation point, the surfactants will form micelles in the solution also. This is how diagrammatically this can be detected. The formation of aggregates like CAC. CAC represent the formation of the surfactant polymer aggregates, and PSP represent the formation of free micelles in the solution. This is how we can determine the various parameters. Again, we have also analyzed the interaction viscosity. We have determined the viscosity and found out the interaction viscosity, interaction between the surfactant and polymers using different concentrations of polymer as well as surfactants, and come to the following conclusions: that critical aggregation concentration of the surfactant decreases, whereas the polymer saturation point increases with the increase in the concentration of the polymer. The viscosity shows that the expansion of the polymer chain expands due to electrostatic repulsion between the surfactant micelles and the polymer chains. The interactions of anionic surfactant like sodium caprylic is more as compared to that of the cationic surfactant, which is cetylpyridinium chloride. And these findings have been published in the following journals. Next part is the micellar and mixed micellar characterization of alkyl dimethyl benzyl ammonium chloride surfactants. These are surfactants, their micellization behavior and their mixed micellization behavior. This is the structure of these alkyl dimethyl benzyl ammonium chloride solutions, surfactants. They are cationic surfactants. And when different type of cationic surfactants, like one is shown as that, other one is in this color, and when they they are mixed together, they form a mixture of micelles. These mixture of micelles perform better in certain applications because in like pharmaceutical applications where either one of the surfactant is very costly or very harmful. So that's why we use a mixture of surfactant in different applications. It also helps to select the most suitable surfactant combination with desired surface activity and the cost. The calculations, this is how we can find out the CMC of the mixture using this formula. These are various parameters, and this equations denote the interaction parameter beta. This is how we can calculate beta depending on the concentration of different surfactants in the solution. Beta values determine whether they are attractive interactions or repulsive interactions or no interactions. If the beta values are negative, then there are attractive interactions between the two surfactants. If beta values are positive, then there are repulsive interactions between the two type of surfactants. Now here in this case, we have determined these beta values and plotted them for various at different temperatures and found that all beta values are negative. It means there are attractive interaction between these type of surfactants. So from these studies, we have concluded that the mixed micelles of these C14, like C14 chain and C16 chain surfactant, show attractive interactions, whereas other two surfactants show repulsive interactions, mixture of two other surfactants. These attractive interactions are more at higher concentration of longer chain length surfactants. Thirdly, if there is a polymer present, then the mixed micelle formation will be delayed. These results of these studies have been published in the following journal. Next is again the mixed micelle formation of a special type of surfactants, because they are called as Gemini surfactants, with some conventional surfactants like single chain surfactants and as well as with polymers. This is called as a Gemini surfactant. A Gemini surfactant, a normal surfactant has one polar head group and one tail, whereas a Gemini surfactant has got two head groups and two chains. This is how it is manufactured. It is mixed. There is a tetraethylene diamine is mixed with respective alkyl bromide, and it is heated and reflux in terms of ethanol.
Sir, you have 2 minutes time to conclude these things. Your presentation, 2 minutes.
Pardon, sir? Pardon, sir? There are only 2 minutes.
More. In 2 minutes,
Okay. Oh, this is how. So there we have find out the
Your books
mixed
conclude
nice.
your.
Okay, so I'm coming to the conclusions. So this is how we can
Yes,
find
yes,
out
yes.
different surfactants. Then we have find out the presence of different co-solvents in presence of these surfactants. Alcohols we have tried, and then like propanol, butanol, tertiary butanol, and similarly we have tried glycols and found the results. And these results, I can conclude these. And different type of surfactants show different behaviors. These results have been published in foreign journals. Then we have tried the non-ionic surfactants called as F16, P105, P123 with series of another surfactant. Again, mixed micellization of these surfactants. And this is how the mixed micellization takes place in case of non-ionic surfactants. They are also used in a number of applications of coating materials. And the results of these work has been published in different journals like this. Then afterwards, we have tried the Gemini surfactants in presence of using different technique, that is ITC, isothermal titration colorimetry. That is very important technique which will determine the critical micelle concentration. And from this, we have determined the enthalpic contributions. What is the enthalpy change associated with the micellization behavior? And using all these parameters, this diagram is for hydrodynamic diameter. How is the size of the different surfactants in presence of different solvents? And these are the various thermodynamic parameters which we have calculated. And the
topic is synthetic textile polymers and their modification. And I am Dr. Asim Kumar Chowdhury from Srirampur, West Bengal. So manufacture of textile materials. So for making textile fibers, it should have certain criteria like good flexibility, extensivity as low as 5% or 50% as per requirement. It should be very fine. The fiber should have very high length to thickness ratio, sufficient strength to resist breakage during manufacture and use, enough thermal and chemical stability. Fibers may be short length called stable, or it is continuous known as filaments. Before invent of synthetic fiber, natural fibers were used, mostly cotton and other cellulosic from plants, shown in on number 1, or wool from body of sheep, and silk from silkworm. These are the main natural fiber. Now the natural fibers, cotton is the oldest and most popular for apparel and garment till today. It's a very hygienic fiber, possesses very useful aesthetic properties, but its plantation record lot of insecticides and pesticides. That means cotton cultivation is have a non-eco-friendly life cycle. Supply is declining day by day because of shortage of cultivation land becoming costlier. Other cellulose fiber are used little for apparel, mostly for non-apparel. Flax was used once for kings and emperors. Durable, this is a very durable fiber. And protein, wool, we know, we must have used all earlier, but now wool is very costly, you cannot afford. There are other hair fibers, alpaca, mohair, Kashmiri, camels, those are used in low extent. Silk is obtained from silkworm and used for delicate textile fabric. Both and wool and silk are quite costly nowadays. Synthetic fiber, 3 most important synthetic fiber used in textile are polyester, nylon, acrylic, contributing 55%, 5% and 2% of the total fiber production. Many other synthetic polymers are also used, but very less extent. Advantage of synthetic fibers are they have high molecular weight and modulus and strength, stretchability, relatively low cost, reasonable stiffness, wrinkle and absorption resistance, convenient processability, easy recycling. Disadvantage, hydrophobicity, less wearing comfort, low durability, poor durability, build up of electrostatic charges, tendency to peeling, difficulty in finishing, insufficient washability associated with hydrophobicity. Since various physical and chemical methods are used to improve the properties of synthetic fibers. Now, most important synthetic fiber is polyester fiber. It is a linear polymer containing 85% of an ester of dihydric alcohol and terephthalic acid. Great varieties of versatilities of polyester are heat state stability, high strength, high modulus, low shrinkage, good light fastness, high chemical and environmental resistance. Most of the synthetic fibers are prepared by melt spinning method. The polymer chips are built, then passed through spinners called spinning, and then drawn or stretched for suitable properties. Polyester fiber is shown in this figure. These are polyester chips. Then these are the spinnerets. Here polyester is spun at 260 to 70 degrees centigrade, addition of fire resistance, etc. And then these holes may be circular, trilobal, pentagon. Accordingly, we get different shape fiber with different properties. This is the filament. Then these are finally this is drawn, stretch. Stretch is required up to 5%, 5 times to its original length for align the fibers in parallel formation from this to this parallel formation. And drawn fiber may be textured or twisted to create softer and duller fabric. Polyester contain about 50% crystallinity. Chemical reaction of during polyester manufacture, all of you know, it is a polyethylene terephthalate by reaction with dimethylene terephthalate and with ethylene glycol. So we get diethylene glycol terephthalate. When blended with cotton, polyester improves shrinkage, durability, and wrinkle profile of cotton. Main drawbacks of polyester are low moisture rigor as low as 0.4%, accumulation of static electricity, high soil pickup during wear, difficult to remove during washing, formation of pins or bunch of fiber on the fabric surface, flammable fiber. Now, peeling is a problem for polyester manufactured material. These are the peels. These are formation of small ball of fiber on the surface of the fabric during washing and wearing. The peeling tendency, this is not peeling. This peeling tendency can be minimized by reducing abrasion resistance so that fiber breaks before formation of large peels. Low peel polyester can be obtained by incorporating terephthalic of barium, calcium, zinc, or organic compound of antimony, iron, or chromium in the polymerizing mass. Hydrophilic polyester. Hydrophobicity is a problem of polyester, so you can make it hydrophilic by adding 5 to 10% sodium sulfate, particle size less than 3 micron, as slurry in glycol during polymerization. Addition of water-soluble aliphatic anomide polyamide may result in polyester increase. Soil resistance can be increased by adding polyethylene glycol or tetraethyl aluminum perfluorooctanate. Improvement of dyeability. There are two ways we can during polyester dyeing. We use a phenolic type compound called carrier. These are hazardous. So carrier free polyester has developed by physical method or chemical method. In physical method, by changing certain changes in melt spinning, drawing, and heat setting operation, or air texturizing and filament mixing. And most important is draw texturizing of partially ornamented yarn. Chemical method, addition of polyethylene glycol, adipic acid, azelaic acid, etc., which form block polymers. TEG is lowered by 10 degrees and can be dyed in deep state at boil in the absence of carrier. Other modifying agents are polyethylene glycol during esterification, polycondensation, and melting. Problem of carrier-free dyeable polyester is that leveling is poor, that is, we get uneven dyeing and lower wash and light fastness. Basic dyes are very bright, but polyester cannot be dyed with that. But once it is copolymerized with sodium salt of 5-sulfo isophthalic acid, it is dyeable with polyester very bright color. But these CD polyester have excessively low melting point and fiber spinning is difficult. These are nylon. Nylons are the synthetic polymers with amide backbones. They may be aliphatic or semi-aromatic. Aliphatic have 85% amide and Aliphatic have less than 85%, and aramid have more than 85% of amide group. There are shown two types of nylon. Their chemistry is shown. This is nylon 6. It is from cactoracrum. It is polymerized in nylon 6 and hexamethylene diamond and adipic acid polymerization gives nylon 6,6. Nylon 6 is produced by ring opening chain growth polymerization of caprolactam in the presence of water vapor, melt span at 250-60. Nylon 6,6 is prepared by step growth polymerization of hexamethylene diamine and adipic acid and melt span at 280 to 90. Nylon 6 is much better in properties, but it is costlier in India. Earlier we are using nylon 6,6 preparing. Now some nylon 6,6 is also produced. DP are around 100 to 250 degrees. Properties of nylon. Nylons are strong and stiff. Recovery from stretch deformation is good. Excellent resilience and recovery of bending. Low density, moderately hydrophilic, moisture again 4 to 5%, soluble in hydrobonding solvents like phenol, formic acid, and benzyl alcohol. Very high abrasion resistance, and that's why it is used in rope making and similar application for materials which are subjected to constant friction. Nylon are fairly resistant to chemical attack. They are attacked by acid base, reducing agent, oxidizing agent only under extreme conditions. Aromatic nylon or aramid,
please conclude, sir. Please, 2 minutes, sir. 2 minutes more.
Okay, just I'll show the slides.
Okay.
Polyethylene, biopolymers, they are prepared just these are prepared biological system instead of synthetic process. They are from developed microorganism, plants and animals. They are biodegradable, can be used for medical purposes. Advantage and others are given. Then biopolymers of high potency are polylactic acid. Summary, now natural fibers are getting substituted by synthetic polymers like polyester, polyamide, acrylic. Polyester is most popular. Polyamide for bright products, material. Polypropylene used for cheaper material. Polyurethane for high elasticity like sportswear, etc. And the synthetic fibers prepared from petrol oils are now substituted by biopolymers. Biopolymers are highly degradable and their at present production is low and mostly being used for medical.
So I am Dr. Bornali Ghosaha. I am a scientist and professor at SN Bose National Center for Basic Sciences, Kolkata, which is an autonomous institution under Department of Science and Technology. Last year also I have presented in the first international conference of this one. And at this time I will be presenting the low power paper electronic based wearable radiation detector by engineering perovskite halide material. So my broad area of research is basically basic science-based research. This is experimental condensed matter and material physics, and it is low temperature physics as well as nanoscience and nanotechnology. So in this part, in the basic science research part, it is I am working on the along with my students growth of materials. We mainly focus. Then we do physics of perovskite oxides and halides. Then we are working also in the semiconductor optoelectronics, microscopy and cross-sectional surface and interface studies, and device fabrication by nanofabrication using different lithographic techniques using E-beam and ion beam lithography. And along with the basic research work, we are also working along with my students the application-driven research that is for technology commercialization. So while working with a sample or material, first thing is the engineering properties of material. So how to engineer the properties of material? You have to able to grow a defect-free and pure with material with proper composition and stoichiometry. Then we have to be able to modify the properties of electronic materials in a controlled and reproducible way. That is the engineering by
Excuse
number of
me.
energetics. Can you hear me?
Your slides are not changing, ma'am.
Not changing.
You are still on the first slide.
Now?
No, ma'am.
Madam, the PPT is not in presentation mode. Kindly put your PPT as a presentation.
Now it's changing. Yes. Yes,
Now?
ma'am.
Now moving?
Yes, now moving.
Okay. So up to which you have not seen this? Second one, this is
Yes.
basic science-based research.
This is broad area research. Yes. Basic science. Yes.
Shall I proceed?
Yes, ma'am.
Okay. So my broad area of research is basic science-based research. I am experimental condensed matter physicist and material physics I am doing. It is a low temperature physics and nanoscience and nanotechnology. So in this a basic science-based research, we are working on the growth of material, physics of perovskite oxides and halides, semiconductor optoelectronics, microscopy and extreme surface and interface, device fabrication by nanos fabrication using lithography techniques using E-beam and ion beam lithography. And along with the basic science-based research, we are also doing application-driven research for commercialization. Now it is comes the third one.
Yes.
Yes, you have to engineer the properties of material while working on this. So engineering properties of material, how one can be do, that is ability to grow. We have to grow the defect-free sample with proper phase and composition and stoichiometry. And we have to be able to modify the properties of electronic materials in a controlled and reproducible way. That is, you have to engineer the properties by a numbering tools. And then after doing all these things, we have to understand the underlying phenomena, and then we have to do the device fabrication for application. And the materials can be any type, this elemental, binary or complex. So, my group is working on some growth of some material either by wet chemistry or physical vapor deposition, by pulse laser deposition or atomic layer deposition. And we are doing some binary oxides, titanates and complex oxide nanowires. We are growing the halide nanowires also, and halide single crystals also. And we are growing thin films of perovskite oxides by PLD or ALD technique. So these are the library of materials our group is working on it. So let us, we are doing the study of physics of perovskite oxides and halides. The structural study we are doing by synchrotron and neutron diffraction experiment. For this experiment, we are going to BRC or ILL Grenoble or Munich, Germany, or the Photon Factory, Japan for structural study. And the low temperature transport property study we are doing in our lab also. And for this, we are doing some lithographic techniques to make the devices, and we are working on a single nanowire device. It is very quite challenging. This is a single nanowire, and we are putting 4-wire contact on it by lithographic techniques and doing the electrical measurement, making the contacts with this. Now, how we do the device fabrication? So from these are the bunch of nanowires. From there, we have to pick up one nanowire. How? We are dispersing in the prefabricated aluminum chrome substrate. This is the contact pairs we made and disperse over here, and we select one nanowire and make contact like this by doing E-beam lithography. And this is the final thing. This is the nanowire, and it is connected with 4 wires. And along with this, we are doing the electrical measurement. And this thing we do by Helios dual beam system in our clean room. So another work my group is doing, that is photo response study. This is the semiconductor optoelectronics. Here we are working on the vertically aligned nanowires and do the cross section. And from this cross sectional study, cross-sectional TM, conventional or ion beam lithography techniques we are using to take the cross-section of a nanowire from a substrate, and we do the compositional study. And we are also working on broadband photodetector UV to NIR 300 to 1100 AM nanometer. This is the cross-sectional sample preparation. These are several steps. The vertically aligned nanowire. First we do platinum deposition, then take cross-section cutting, and then do lift off by OmniProbe. And after taking this piece, we are just mounting in the OmniProbe grid. This is a general grid we are doing for the TEM study, but this is the OmniProbe grid. Here you have to mount the sample and to see the cross-section and do the study. These are the different steps of it. Now, let us come to the original presentation. This is we are doing the technology commercialization development related work also. This is the Department of Science and Technology project. This is called TRC, and we are working on in this project also along with my students. This is our main motivation, making us effective in the innovation space. The primary focus is on healthcare, environment, and material industry, and make the output relevant to the societal needs in addition to its value in commercial space. Now, we have made several prototypes: visual ammonia sensor, 10 ppm, electrical ammonia sensor, nitric oxide sensor, and PZT nano generator. This is a power generation from waste energy. And almost all the patents has been granted in all these areas. Now we are working on the radiation detector. This is funded by Department of Science and Technology. This is under TRC project. So in this project, we aim to investigate some of the important science as well as multidimensional application potential of solid-state perovskite halides. Novelty of this work and challenges. What are the challenges? Perovskite material we are growing as a single crystal, everything. But growing on a substrate like paper is challenging. That is why we could make a flexible or wearable detector. And making paper electronics based solid state detector in three important areas we are making: gas detector, photo detector, radiation detector. Today I will be telling about the radiation detector, but I will show one slide on gas detector also. So let us see the gas detector, ammonia gas detector we have made. This is the actual color grown. It is grown on paper and mounted on a in the form of watch. Anyone can wear it, and if we put ammonia on it, its color is changing. Similar thing is that if we put in a tape, color is changing. So this is the beauty of this. This is a visual ammonia sensor, and it is act like a pH paper. So it is a portable, standalone, and fast response flexible wearable sensor. It is called ammo paper. Any layman can detect ammonia. This patent has been also granted, and assignment deed has been done with NRDC along with our center in New Delhi on 2nd March. So it is ready for commercialization. Now, and this is the beauty of this sensor. This, as we go on increasing the concentration, and it is sensing within 4 to 4 seconds, give a visual warning. That is the beauty. No machine, no nothing connection, no nothing is needed. Only visually you can see that area is ammonia polluted, and you have to leave the place, or you have to take care of you. Then I am telling about the gamma ray detector. This is a radiation detector. This is solid state perovskite halide material has been grown on paper. This is a flexible and wearable paper detector. What is the state of this art of this? The proof of concept has been established towards the cost-effective, room temperature, and highly radiation-resistant solid state gamma ray detector. And necessity, why it is necessary to make a radiation detector and related issue. What are the related issues? There are several areas like nuclear imaging, cancer therapy, security checking, where needs radiation detector just as a quick tracer of presence of gamma radiation. In most cases, detection of gamma ray photon only by conventional energy resolution technique, which requires special arrangement like gamma spectrometry or nuclear instrumentation, which are not very easy tool and for rapid detection. You have to make very good setup and low temperature thing. All these things are required. But in our case, it is very easy. It is a deviated approach we are following, not by energy radiation, rather than via electrical readout method at room temperature using perovskite halide paper detector as a quick marker of gamma radiation. This detected technique would be extremely useful in radiation-prone areas in a cost-effective way, where fine energy resolution is not a primary concern. Am I audible? Hello,
Yes,
sir?
yes, ma'am.
Okay.
You are audible.
Okay.
Yes, ma'am.
Dr. Ghosh, sorry to
Yes.
interrupt you, ma'am. We have restricted time with us. And
Yes,
the
yes,
next
yes.
session-
I am almost done.
And Dr. Tejender, please stick to the time.
Yes.
Only 12 minutes are given to each and every candidate.
Yes,
Okay.
ma'am. Yes.
Okay,
Okay,
sir,
I
thank
don't
you.
have any problem. Okay. We are using the cobalt 60 source, 1 kilocurie activity, and then we can detect current at this rose rate of 0.33 in cycle per second. And from this, we have calculated different voltages, photocurrent. And this detection technique could be extremely useful in radiation-prone areas in a cost-effective way, where fine energy resolution is a not primary concern. So, important novelty of this work is paper electronic based, and this is flexible and wearable, and room temperature operation and simple, quick and direct detection can be done, and it is operable in a wide range of gamma photon energy and a low detection capability down to 0.01 nanocurie level, and operable and 1 volt DC bias and photocurrent of 1 nanoampere, and fully compatible with low power and high radiation sustainability and good mobility lifetime and very low cost. And mobility lifetime product is a fundamental figure of merit of radiation detector. So this is the structure and this is the morphology. And this is the actually device. This is a and this is the original device. And on top of it, we put the electrical contact and do the measurement. This is the lifetime, real-time current response paper detection as a different dose rate. And this is the after we check that radiation sustainability of our detector. The cumulative dose 1.6 kilo gray, it has been given for 1 hour. So after and before exposure, both structure is stable. There is no problem, and also it is bended, and you can see bended for 3 millimeter. But there is no not at all in different changes before and after. So it is robust also. So and it is comparable with the available single crystal detector in the market. So the this halide based flexible wearable detector shows excellent structure and mechanical robustness under high energy with sufficient long exposure. So we have also made several detectors. I have already told nitric oxide, and all this patent has been granted. So this is also P80 nano generator from waste energy. It has been done. So this is my acknowledgement that I am working with my students. So I am thankful to all of them in my laboratory, and I have thankful to my collaborators. And we have some international collaboration also. And I am thankful for financial support to Department of Science and Technology and ICRTMD and our center facilities. And this is my group, and I have presented my students' work. His thesis is just getting awarded. Thank you all for your kind attention.